All right, today we're jumping into a paper that really caught my eye. It's called VideoAuto-R1. Video auto reasoning via thinking once, answering twice.
Yeah, this one tackles what is, frankly, one of the biggest operational headaches for anyone working with multimodal large language models for video.
Which is the fact that chain of thought, cuck-T reasoning, it's just so slow.
It's slow, it's computationally expensive, and as this paper points out, a lot of the time it's completely unnecessary.
And that's the core problem they're solving, right? The idea that for video, which is so perception heavy, forcing a model to always think out loud just doesn't always give you a better answer.
Exactly. Sometimes it's even worse. So their solution is this framework, VideoAuto-R1, which is all about being adaptive. They call it an auto-thinking strategy.
A reason when necessary approach.
Precisely. And they build this around a really neat paradigm. Thinking once, answering twice. During training, the model gives an initial answer, let's call it A1, then it does its reasoning, and then it gives a final reviewed answer, A2.
And then at inference time, it gets really efficient. The model just looks at its own confidence in that first answer, A1, and decides, do I stop here or do I need to run the full expensive QT process?
And the results really validate the whole approach. They found it correctly activates that reasoning mode way more often for complex tasks, about 51% of the time on video MMU, but keeps it low, like 25%, for simpler perception stuff.
And the headline number has to be the efficiency.
Oh, absolutely. They cut the average response length by a factor of 3.3. We're talking from around 149 tokens down to just 44. That is a major, major saving.
And that reduction in token count is really the whole motivation here. For the last couple of years, it feels like QT has been treated as this silver bullet.
The gold standard, yeah.
It solved math, it solved coding, and the assumption was just, if you want a model to be smarter, you make it show its work.
Yeah. But video just breaks that rule. The whole nature of understanding a video is fundamentally different from, say, symbolic deduction. A math problem needs logical steps. A video problem, it needs good visual perception first and foremost.
Wait, let's just pause on that because it feels almost like heresy. Are they really saying that chain of thought, the thing that revolutionized LLMs, can actually be a bad thing for video tasks?
Not a bad thing necessarily, but redundant. It's a real indictment of the unconditional use of QT. Their study looked at state-of-the-art models, Video R1, Time R1.
The big names.
The big names. And they found these models often performed just as well, and sometimes even a little bit worse, when they were forced into that verbose, always thinking mode.
Why do you think that is? Is it just the model overthinking what it's seeing?
That's a great way to put it. I mean, if the visual signal is a bit noisy, or if your initial perception is already spot on, what good does generating a long, rambling text explanation do?
It could just introduce more noise, hallucinations even.
Exactly. It's like trying to talk yourself into seeing something more clearly. It doesn't work. Yeah. What you actually need is better visual input, not more words about the fuzzy input you already have.
And the cost of this always-on thinking is just huge, especially if you're thinking about putting these models into production.
It's immense. The paper mentions QT responses hitting, 386 tokens on average for some models. In a real-world application, that latency kills you. Every single one of those tokens adds up.
And for all that cost, on perception-heavy benchmarks like Video ME, they found you get basically zero improvement in accuracy.
Zero. So the conclusion is pretty stark. Blindly forcing every query through a QT process is operationally crippling, and for a lot of video understanding, just plain redundant.
So it seems like QT really only earns its keep in these very specific niche video domains.
Right. They found the only place it consistently provided a real tangible boost was on benchmarks like Video MMU.
Which has a lot of instructional videos, right? Math problems, physics demos.
Exactly. The kind of content where the visual is just a setup for a symbolic deduction problem. In those cases, you genuinely need the multi-step reasoning. And that's where QT shines. But that's not most video.
So this brings us to the core of their solution. How do you build a model that knows when it needs to reason? I know previous attempts at this kind of auto-thinking have been, pretty unstable.
Yeah, they often suffered from something called mode collapse. The model would just learn to always pick one mode, either always think or never think, which totally defeats the purpose.
So how does VideoAuto-R1 get around that?
The shift in thinking is pretty clever. They completely eliminate the need for any kind of special switch token or a hard binary decision during the training phase.
Instead, they just force the model to always output the full sequence.
Always. The initial answer, A1, the reasoning part, and the final reviewed answer, A2. It's a unified format. Boxed I think, boxed a day.
So by doing that, the model learns two skills at once. It learns how to make a quick guess, and it learns how to critique and refine that guess.
Exactly. And the really critical decision of whether to use the reasoning part, that's deferred entirely to inference time, where you can make a much cheaper, faster choice.
And they achieve this stable training using group relative policy optimization, or GRPO. So this is reinforcement learning, right? They're not just showing it examples, they're scoring its behavior.
Right. And the design of the reward function here is what's really fascinating. They call it the dual answer reward. The total score the model gets is a weighted sum based on the correctness of both answers.
And this is where that subtle but critical detail comes in, the asymmetric weighting. They set the weight for the final answer, A2, to be higher than the weight for the first one, A1.
Yeah, like 1.1 for A2 and 0.9 for A1.
Why is that small difference so important?
It's all about creating an incentive for self-correction. By making the final answer worth more, you're telling the model it's more important to end up correct than to be correct right away.
So a wrong to correct sequence gets a higher reward than a correct to wrong sequence.
Exactly. It structurally pushes the model to develop a robust reasoning process that can fix its own initial mistakes. It makes the thinking step truly accountable.
That stops the model from just getting lazy and always trusting its first guess.
Absolutely. And they also have a smart way of handling problems that are just too hard to guess up front.
Right, the fallback bonus.
Yeah. If the model knows a problem needs serious thought, it can just output a specific phrase in that first answer box. Something like, ugh.
Let's analyze the problem step by step.
Right. And by doing that, it gets a small reward for being honest, for admitting it needs to think first. It stops the model from just throwing out a random low-confidence guess on a hard problem.
Okay, so the training produces this robust, self-correcting model, but the whole point was efficiency. How do they turn this into a super fast system at inference time?
That's where the early exit mechanism comes in. And it's surprisingly simple. It's just a rule-based check that happens at test time.
So after the model generates that first answer, A1, it just pauses.
It pauses and calculates a confidence score for that answer.
And how does it do that? What is a confidence score in this context?
It's just the length normalized mean log probability of the tokens in that first answer. In simple terms, the model is just asking itself, how certain was I about the words I just generated?
And if that certainty is above a certain threshold?
Which they set to 0.97. If it's above that, the model just says, yep, I'm confident enough, and it terminates right there, returning A1.
Saving all the time and tokens it would have spent on reasoning.
But if the score is lower, the model says, oh, my confidence is a bit shaky here. I better think this through. And then it proceeds to generate the full reasoning trace and the revised answer, A2.
It's like a triage system for questions. Simple perception query, get immediate answer. Complex probability problem, straight to the full diagnostic.
And the data shows it works beautifully as a dynamic resource allocator. On the easier perception-focused benchmarks, the model's initial confidence was naturally high.
So the thinking ratio stayed low.
Just 25%.
Yeah.
And all those tasks, forcing it to think, only gave a tiny 0.1% accuracy boost. So not worth the cost.
But on the hard stuff like video MMU,
the initial confidence plummets. It drops to about 0.874, which forces the thinking ratio way up to 51%. And that extra computation pays off. It delivers a solid 4.0% accuracy gain. It's spending the budget exactly where it's needed.
They had that great qualitative example in the paper, didn't they? The conditional probability problem.
Yes, finding P of X less than 3.5 given X is less than 4. The model's initial guess was wrong, let's say option D, but its confidence was only 0.92.
Below the threshold.
Below the threshold.
Yeah.
So that low confidence immediately triggered the full reasoning. The model then generated this detailed COT trace, calculating the PDF, the CDF, all the symbolic steps.
And that allowed it to correct its answer.
It revised the final answer to the correct option, C. It's a perfect illustration of how that second-chance reasoning-driven answer can fix an initial error, but only when the model's own confidence flags it as necessary.
When you talk about cutting the average response length by 3.3x, from 149 tokens to 44, that isn't just a research finding. For anyone trying to deploy these models, that's a massive operational win.
And it comes without sacrificing that top-tier performance. VideoAuto-R1 still achieved state-of-the-art accuracy. It actually improved the video MMU score by nearly 4 percentage points.
And it seems like the approach itself is pretty generalizable. They saw improvements on image benchmarks too, like MathVista.
Which is really important. It shows that this dual answer training via RL is a robust way to inject critical reasoning skills into these models, not just for video, but potentially for other modalities too.
Now, here's where it gets really interesting for me, and it maybe points to the limits of this approach: the results on temporal grounding tasks.
Yeah, things like charades, STA. These are tasks where the model has to find the exact start and end time of an action in a video.
And what did they find there?
They found that for those tasks, the initial answer, A1, was basically always good enough. The final reviewed answer, A2, provided almost no measurable benefit. The accuracy scores were identical.
That tells you something really fundamental, doesn't it? It says that language-based reasoning hits a wall when the problem is about refining a purely visual or temporal feature.
Exactly. If your visual encoder got the timestamp slightly wrong to begin with, no amount of talking about it in a text-based QWERTY is going to fix that underlying perception error. You're just reasoning about the wrong data.
But it does prove the efficiency of their framework again. For grounding, the model can just default to the early exit and save a ton of tokens without losing any performance.
Right, but it also shines a spotlight on the limitations of textual reasoning for solving visual problems.
So if we pull this all together, VideoAuto-R1 seems to have really solved this efficiency versus accuracy trade-off. It takes QWERTY from being this mandatory, expensive process and turns it into an adaptive resource that the model uses intelligently.
It's about making these powerful video models actually practical and affordable enough for real-world use cases, like real-time summarization or analysis.
But those temporal grounding results leave us with a bigger question. They clearly show that for these fine-grained visual tasks, just thinking harder with words isn't the answer.
Right. Textual reasoning can't fix a perception error after the fact.
Which means the paper is hinting at what has to come next, something they call interleaved multimodal reasoning.
Exactly. This is the idea that the reasoning process can't just be generating text. The model needs to be able to go back to the source. It needs to be able to revisit video frames or reanalyze visual features during the reasoning step itself.
So it's not just thinking about what it saw, it's actively looking again as it thinks.
Precisely. And that really leaves you, the listener, with a provocative question for the future of this field. If we've hit the ceiling on what language-based QWERTY can do for purely visual tasks, how do we build the next generation of models that can truly think with vision and language at the same time? It really feels like that's the next great frontier.